At the end of this online module, you should be able to code a selection structure, convert between selection structure representations, language, flowchart, and code, create test cases to evaluate a selection structure, and track the execution of a single selection structure. We will start with a simple problem to learn about selection structures. You are part of a team testing airfoils for optimal flight speed. Your teammate determined a Mach number for each airfoil's maximum flight speed using data from wind tunnel tests. You must develop a program to classify each airfoil based on its Mach number, subsonic, transonic, or supersonic. This problem requires code that identifies the classification based on the speed entered. Up to this point, we have only done sequential coding, meaning that each command is executed in the order it appears in the code. Selection structures branch code based on a logical condition, and repetition structures execute commands multiple times based on a logical condition or by setting a counter. This module is concerned with the selection structures. This is the general form of a selection structure. Selection structures always begin with an if command and a logical condition. If the logical condition is true, then MATLAB executes the group 1 commands and skips all other commands until after the end command. If the condition with the if is false, MATLAB moves to the else if command and checks its condition. Notice that else if has no space. If the else if logical condition is true, then MATLAB executes the group 2 commands and skips all other commands until after the end command. There can be as many else if commands as needed in your selection structure, but each one needs its own conditional expression. If it is false, MATLAB moves to the else command and executes the group 3 commands. Also, notice that else does not require a condition, which means you only use one else command in a selection structure. It is only executed when all other decisions are false. That is also why it is on the false path of the flowchart. Now, going back to our simple example, let's walk through the translation of language to flowchart to code. First, I'm going to give simple language to what needs to be done. We need to input a Mach number from the test results. Then use that input to make decisions. We will select subsonic if the Mach number is less than 0.8. Select transonic if the Mach number is between 0.8 and 1.3 inclusive, or select supersonic if the Mach number is greater than 1.3. Finally, we will output the appropriate category. Looking at this as a flowchart, we see that the first step in our language translates to an input in the flowchart. Then we make the first decision. Is the Mach number less than 0.8? If yes, we display subsonic. If no, we ask the next question, is the Mach number between 0.8 and 1.3 inclusive? If the answer is yes, then display transonic. Then notice that for step 4, we don't have to test the conditional there because all other possibilities have already been tested. This means that we can display supersonic if the answer to both of the other questions are no. Now, to convert the flowchart to code, each element in the flowchart represents part of the code. We can think of the words and order the flowchart as pseudocode. For this first input, we can either hard code the number in each time we run it, or we can ask the user to provide that information with the input command as seen here. Then the first decision is coded with the if and the condition represented by the question. When that condition is true, we display subsonic. Otherwise, we move to the next decision, which is the else if statement. When the condition on the else if is true, we display transonic. Otherwise, we continue to the else statement and display supersonic. There are many variations of selection structures. This first variation is the if-end structure. Notice at the decision point, if the condition on the if is true, it executes commands in group 1. If the condition is not true, the program does nothing within the selection structure. A second variation is the if-else-if-end structure. At the first decision point, if the condition on the if is true, it executes commands in group 1 and skips all other commands until after the end statement. If the condition is false, it moves to the next decision, which is an else if. It executes the commands in group 2 and moves on to the commands after the end statement. If the else if condition is not true, the program executes nothing within the selection structure. Another variation is the if-else-end structure. Notice at the decision point, if the condition on the if is true, it executes commands in group 1. If the condition is not true, the program executes the commands in the else statement, which are the group 2 commands. Let's try a more complicated problem to learn about how selection structures behave in MATLAB. Environmental engineers often work to assess damage after small bodies of water have been contaminated by chemical spills and runoff. While on site, the engineers often need to assess the volume of water in the lake or reservoir by the height of the water. They need a simple program to output the estimated volume if they know the height of the water. The 3 simple geometric physical models they use to quickly estimate the volume of the water are rectangular prisms, cylinders, and hemispheres. Just like in our first example, we will work through the problem using language, then a flowchart, then code. First, we will need height of water in feet. We will also need to decide which 3D model to use, the rectangular prism, the cylinder, or the hemisphere. Once that decision is made, we may need to get additional measures based on the shape. If it is a rectangular prism, the volume is length times width times height. We have only asked for the height, so we need to ask for the estimations of length and width. If cylinder is chosen, the volume of the cylinder is pi times radius squared times height. Again, we only have height, so we will need a radius estimation. If hemisphere is chosen, then we won't need any additional information. That is because the volume of a sphere is 4/3 pi r cubed, making a hemisphere half of that, or 2/3 pi r cubed. Since the height would represent the radius, we don't need to ask for anything else from the user. And for whichever shape is chosen, we need to calculate volume. Finally, we need to give the user the estimated volume in feet cubed. To translate this language to a flowchart, let's consider how each step will need to happen and in what sequence. First, we will begin our flowchart with the terminal start. Then we will need to input height of the water. That is shown with a parallelogram and the corresponding pseudocode. Pseudocode is language that represents the actual code, but written for humans. This means that there are not MATLAB-specific functions or syntax included. So inside the parallelogram, we see input height in feet. Next, we need to decide which shape we are using. So let's first decide if we are using a rectangular prism. That decision is a diamond, and we can add the question, is shape choice a rectangular prism, in the diamond. If the answer is yes, then we need to get additional information. That is, we need the length and width estimations. So we add a parallelogram for the inputs and appropriate pseudocode. Following that path in our flowchart, the next thing we need to do is calculate the volume of the rectangular prism. That is a process, which gets a rectangle in the flowchart. If the answer to our question, is shape choice a rectangular prism, is no, then we need to decide if it is a cylinder. So we add another diamond and ask the question, is shape choice a cylinder? Again, if the answer is yes, then we need to get additional information. That is, we need the radius estimation. So we add a parallelogram for the input and appropriate pseudocode. Then we need to calculate the volume of the cylinder. Again, that is a process which gets a rectangle in the flowchart. If the answer to, is shape choice a cylinder, is also no, then we know it is a hemisphere. So we can calculate the volume of the hemisphere, putting the appropriate rectangle in the flowchart to represent this. Finally, we need to provide the user with the estimated volume, which is an output. So we add the parallelogram with pseudocode representing this output. And with every flowchart, we need to end the flowchart with our terminal stop. Now let's translate our flowchart with pseudocode into MATLAB code. Looking at the flowchart, we need to input the height of the water in the reservoir. Like in the last example, let's ask the user to input each value we need as we need it. Using good programming standards, our variable will be height_water, and we will ask the user to input the estimated height of the water in feet. Now we need to have the user input which shape they want to use to estimate the volume. We can start with some directions to the user, then add the code to let the user input their shape choice. The selection structure is part of the calculations section. So let's add commenting to show the goal of the structure and then continue to work our way through the flowchart. Our first decision asks if the shape chosen is a rectangular prism. That corresponds to if shape_choice equal, quote, rectangular prism, end quote. Now, if that is true, we need to get the input for length and width, which we can ask the user for using the input function. And then we need to calculate the volume of the rectangular prism. So I will make volume_water equal to the formula for volume of a rectangular prism. Now, if the shape choice is not rectangular prism, we follow the no path of the decision diamond and consider if the shape choice is a cylinder. This is not a new if. Rather, it is an else if, because we have already eliminated the rectangular prism as a possibility. Else ifs have a conditional statement. Here it is shape underscore choice equal equal, quote, cylinder, end quote. When this condition is true, we need to input the estimated radius and calculate the volume. This code is very similar to the code for the rectangular prism, so I am going to copy and paste that code and modify. Modifying the comments, we only estimated the radius of the surface of the water. In the code, I change the variable name to radius underscore water and modify instructions to the user. In the comments here, I change rectangular prism to cylinder, and in the code, I modify the equation appropriately. When the answer to whether or not it is a cylinder is no, we know that the user did not choose rectangular prism or cylinder, so the only choice left is hemisphere. Therefore, this is represented by the else statement, and we can just code the calculation of the volume of the water when hemisphere is chosen. We must always finish our selection structure with an end statement, so MATLAB knows what code goes with each choice. That way, if one of the decisions before is yes, MATLAB will only skip to end and not skip all the remaining code in the program we might need. For this code, we need to output the volume of the body of water. Since we named all three calculations volume underscore water, we can print that to the screen using fprintf with appropriate decimal places and units. Now let's make sure to develop test cases that will traverse all paths in the flowchart, and therefore also our code. The first path is when the user chooses a rectangular prism. I'll let the height entered be 5 and shape choice be rectangular prism. We will need to input a length and width, so let's let the length be 10 feet and width be 4 feet. We know length times width times height gives us 10 times 4 times 5, which is 200 feet cubed, so this is what we expect from our program. The next path is if we answer no to rectangular prism, but yes to cylinder. Again, we can set the height to 5 feet. The shape choice is cylinder. Our additional measure is the radius. Let's let it be 10 feet. Using a calculator, pi r squared times height gives pi times 10 squared times 5, which is 1,570.8 feet cubed. The last path is if we answer no to both rectangular prism and cylinder. Again, let's set height to be 5. The shape choice is hemisphere. There are no additional measures, and 2/3 pi r cubed gives 261.8 feet cubed. Let's run the code with these different test cases and track the outcomes. Enter estimated height of water in feet. We decided to use 5. Press enter. The shape we need to choose first is rectangular prism. Press enter. Ooh, an error. It says that we have an invalid expression. Oh wait, the directions told me to put it in double quotes. We did not discuss this earlier, but that is so that shape choice will be a string variable. I'll re-enter that with quotes. The estimated length of the surface is 10, and the width is 4. And we get the expected result of 200.00. Let's do the same for case 2. I will clear my workspace and run the program. I enter 5 for the height, choose the shape cylinder in quotes, and enter 10 for the radius. That gives 1,570.8 feet cubed. That is what we expected. Finally, case 3. Again, clear the workspace and run. Enter 5 for height, choose hemisphere in quotes, and we get 261.8 feet cubed. This is great. The cases all ran as expected. But I wonder what would happen if I put a different shape than the 3 listed. So let's make another case. Let's do cone. We would hope that this will give us an error, so we don't expect additional measures to be requested. Let's run the code. I put in 5 and cone in quotes. It doesn't give me an error, and the output is the same volume as the hemisphere. Let's take a look at our flowchart to see if we can figure out why. Starting at the beginning, we input 5 feet for the height and cone for the shape choice. That would make the first decision no and the second decision no. Then MATLAB will calculate the volume of a hemisphere. So this means that if we put anything other than rectangular prism or cylinder, spelled correctly, our program would output the volume of a hemisphere. Okay, let's fix that. We can do that by changing what happens at the No decision on the cylinder choice. Let's make another decision to check if hemisphere was chosen. If yes, we can calculate the volume of the hemisphere. But if no, let's have the code output an error in shape choice. Then, outside of the structure, we can output the volume. With this change in the flowchart, we can easily modify our code. Everything about the code is the same until the No choice on cylinder. Since there is now a need to check for the hemisphere choice, we can change this else to else if and add the conditional for hemisphere. Now there's a new else. So if the user doesn't enter any of the 3 required shapes, we need to tell the user that their input doesn't make sense. We can add an fprintf statement to tell the user that they need to choose a shape listed and that spelling matters. fprintf has a special FID code that is the first input. If you don't use it, it assumes it's a 1, which is the standard output. If I put a 2 here, MATLAB knows this is a standard error statement and will make it red. So I'm going to use that here. Then end the selection structure. Looking at this fprintf statement, which is outside the selection structure, notice that there is a variable volume_water that needs to be defined so the program will run to its conclusion. So we can also add a dummy variable in the else with nothing in it to allow the fprintf statement in the format section to run. We can't leave it completely blank, so either use empty brackets, which is a matrix size 0 by 0, or use quotes, which I did here. Since we recoded this, we should recheck all cases. But for now, let's just check the case where something wrong is entered. I run the program, put in 5 for height and cone for shape choice, and I get my error. This is great. In summary, we learned to code a selection structure to address all necessary paths for a given problem. We learned about the different forms of selection structures and that there can be multiple else ifs in a selection structure. We also converted between selection structure representations, language, flowchart, and code, then created a thorough set of test cases to test all possible paths in the selection structure, and we even added an extra case to help us correct our program. Finally, we tracked each test case by identifying the correct path given the input and checked that the actual output matches the expected output.